Hello everyone, my name is Nicole Starrett, and today I will be presenting near-field drone measurements for broadcast antennas. Before we begin, I want to take a minute to make a special acknowledgement to two groups who were instrumental in developing this near-field drone measurement technique I'll be discussing today. First, Cavell Mertz and Associates for their help developing the near-field process from the very beginning, including collecting and analyzing near-field drone data from multiple sites. And second, Eric Wandell with Wavepoint Research for helping to both develop and promote this near-field drone measurement process. Without their help, this process would not be where it is today. Here's a quick overview of what I'll be discussing today. I'll start with field pattern verification and why it is important for broadcasters. Go over the current methods for performing field pattern verification. I'll then define the near field versus far field for broadcast antennas, how we can modify current drone methods for use in the near field, the HFSS software we use for near field analysis of antennas, a few examples of data analysis in HFSS in comparison to the real world drone data, and finally, a summary of this near field drone measurement technique. So why do we do field pattern verification? Well, first and foremost, is your programming reaching its intended audience? Is the antenna itself hitting the eyeballs you want it to hit? Is your antenna operating as expected? Is it installed correctly and in the correct orientation? Also, if you have an older antenna that is not performing as it once did, what issues might that antenna have? Most importantly, field pattern verification is a reimbursable repack item. So if the FCC is paying for it, why not double check everything? So what are our current choices for field pattern verification? First, we have ground-based measurements. These measurements, whether taken from a sophisticated measurement van or from an antenna on a pole with a field strength meter, are a standard industry tool. However, with FCC requirements of a mobile run of at least 100 feet, about 30 feet off the ground, this measurement process can be quite time-consuming. Also, ground-based measurements have built-in errors due to multipath, time-varying signal strength, and ground effects or reflections. We also have aerial measurements taken by helicopter or drone. I won't get too much into helicopter measurements today as they take a great deal of planning and are cost prohibitive for many broadcasters. Drone measurements, on the other hand, are much simpler to implement and are becoming more commonly used. I'll get into this in a little more detail in the next few slides. Drones have increased in popularity across many industries and are an excellent tool for field pattern verification. Drone measurements are quick to perform and cost-effective. They also eliminate the statistical analysis needed for ground-based measurements. Despite their benefits, drones come with a few drawbacks, most of which are imposed by the FAA. The FAA has certain restrictions on flying drones for commercial use. These are listed in Title 14, Chapter 1, Subchapter F, Part 107. These regulations include everything from operating from a moving vehicle to operating over people and have a strict definition for line of sight for drone pilots. The regulation I'll be discussing today, or I'll be focusing on today, is Part 107.51, Operating Limitations for Small Unmanned Aircraft. This regulation includes a height restriction of 400 feet above the ground, unless you're operating within 400 feet of a structure called the structure's shield. Any measurements that need to be taken outside of the shield require a waiver. The waiver process itself can be complicated, depending on your measurement needs and the site location. All appropriate regulations from Part 107 need to be selected on your waiver forms. You need to demonstrate that the flight can be conducted safely by identifying all hazards and mitigating the risks associated with each hazard. All required documentation, including a flight plan, must be submitted, and once it is submitted, cannot be amended. Then once everything is turned in, there is a waiting period of up to 90 days for the FAA to process your request. Due to these restrictions, the quickest and easiest way to use drones for field pattern verification is to operate within the 400-foot shield of the tower. I'm going to take a few minutes here to define the near field versus the far field of an antenna and discuss how these regions can affect field measurements. The far field of an antenna boils down to the distance from the antenna at which the radiation pattern no longer changes with distance. As you can see from the figure and the equation on this slide, the far field region will be different in the azimuth and elevation patterns for the antenna. Radiation patterns measured inside of the far field limit or in the near field are not yet focused and will have different characteristics than a typical far field pattern. Let's picture a typical top-mount UHF pylon antenna, about 14 inches in diameter and approximately 50 feet tall. At 600 megahertz, the azimuth pattern far field will begin at about 1.7 feet from the antenna. However, the elevation far field will begin around 3,000 feet from the antenna. So if you were to measure this antenna with a drone inside the 400-foot shield of the tower, you would have no issues measuring the far field azimuth pattern. The elevation pattern measurement, on the other hand, would be well within the near field of the antenna. Now you may be thinking, okay, the elevation pattern will be a little unfocused, but how far off could it really be? Take a look at this plot showing the calculated elevation pattern of an antenna at varying distances from that antenna. The dotted line is the far field elevation pattern, and the solid lines are elevation patterns at varying distances up to 400 feet from the antenna. You can see that too close to the antenna, as shown in the solid blue line on the slide, the radiation is completely unfocused. The farther out you move, the more defined the pattern becomes. But even at 400 feet, the elevation pattern can vary significantly from the desired far field pattern. Let's do a quick recap of our field verification options. There are ground-based measurements or helicopter measurements, each with their own drawbacks. Then we have drone measurements, which can either be taken inside the shield of the tower or outside the shield of the tower if you obtain a waiver. Plus, we know from the previous slides that any elevation pattern measured inside the shield of the tower will be unfocused until you're in the far field of the antenna. Now, for those of you thinking, even though it will take longer, I should apply for a waiver and get the most accurate measurement I can, right? Well, let me tell you a little bit about multipath and how it can affect drone measurements in the field. Ground reflections and multipath affect the accuracy of elevation patterns measured with a drone from a distance. In general, the larger the distance, the smaller the reflection angle, and the larger the measurement error. For practical purposes, we can assume no energy is directed toward the ground in the very near field of high-gain antennas. So the least error-prone position to measure the elevation pattern is within the 400-foot shield of the tower. So how do we modify the current drone measurement method for the near field to get quick and easy measurement with as few errors as possible, but also be able to compare that measurement to the desired far field pattern? From a drone operator standpoint, this is relatively simple. Just fly the drone at 400 feet from the antenna, stay within the shield of the tower. This eliminates the need for more time-consuming and cost-prohibitive measurement techniques. The only glitch is we need a way to analyze the near-field data and compare it to the factory-measured data for that antenna. Lucky for us, the near-field data can be calculated with the use of ANSYS HFSS software. HFSS is a 3D electromagnetic simulation software tool used to evaluate high-frequency electronic products. Every slotted coaxial antenna manufactured by Dielectric for repack was designed using HFSS. HFSS breaks each model down into a mesh of thousands of tetrahedra, as shown in the pictures on this slide. Then Maxwell's equations are solved at each vertex or node on the mesh. These are exact calculations at each node, not estimates. Within HFSS, a full broadcast antenna can be modeled as designed and tested in the factory. This requires a full knowledge of all antenna features to construct the most accurate antenna model possible. For example, each layer of the slotted coaxial antenna is unique, which should be reflected in the HFSS model. Coupling structures, dipoles, slot lengths, pattern shapers, etc. all need to have precise dimensions to calculate the antenna radiation characteristics. Here we have a few example models in HFSS. Top-down views are on the left, while isometric views of the antennas are on the right. Top-mount antennas are relatively simple. The model consists of only the antenna components as seen on the far right. As seen in the other pictures on the slide, side-mount antennas are a different story. Everything in the aperture of the antenna must be modeled. This could include the tower itself, transmission line or waveguide, climbing ladder, support poles, or any other antennas at the same elevation level. Once an antenna has been modeled, the far field elevation pattern is calculated and compared to final factory measurements for the antenna, as shown here. The factory measured far field elevation pattern is shown in blue, while the HFSS far field elevation pattern is shown in red. The beam tilt is consistent between the two patterns, and the null structure is similar. This validates the functionality of the HFSS model. Since HFSS produces a full 3D electromagnetic solution for the antenna, a near-field sphere can be placed around the antenna at a user-selected distance to calculate the near-field radiation characteristics of the antenna. The near-field elevation pattern for the antenna is calculated at points on this sphere, as shown in the red line on the slide. It's important to note here that the antenna center of radiation must be precise between the drone measurement and the HFSS model. Otherwise, the elevation pattern can be skewed significantly. This plot shows the beam tilt variance for near-field pattern between the drone and HFSS measurements when the center of radiation is changed. Even a discrepancy of a few feet can significantly impact the beam tilt of the antenna. Next, I'm going to go through a few examples of drone measurements compared to HFSS near-field data. Here's our first example. This data is collected from a side-mounted 10-layer DSC pylon antenna at channel 36. The blue trace is the drone measured elevation pattern, while the orange is the HFSS calculated near-field pattern. As you can see, the beam tilt and null structure for both of these measurements correlate. Here we have the azimuth pattern comparison for the same 10-layer antenna. The horizontal polarization is shown on the left, while the vertical polarization is shown on the right. In both plots, the HFSS pattern is shown in red, while the drone measured pattern is shown in blue. With a side-mounted antenna, the azimuth pattern is affected by everything in the aperture of the antenna, so the variance between the two patterns is realistic from a perfect computer modeled tower and antenna to the real world. Our second example is another side-mounted 20-layer DSC pylon antenna at channel 30. This one is mounted on a support pole at the top of a tower. As with the previous example, the beam tilt and null structure between the two measurements correlate. These are the azimuth patterns for the 20-layer example on the previous slide. Notice in both the horizontal and vertical polarizations, the support pole and the antenna is mounted to has far less of an effect on the azimuth pattern than the tower did in the previous example. Our third and final example is a top-mounted 20-layer pylon antenna operating at channel 32. Once again, our near-field beam tilt and null structure correlate between the two measurements. You notice the beam on this antenna appears to be more on focus than the previous two examples. This is due to the length of the antenna. Since the 20-layer antenna is much longer than the other two, the near-field region for this antenna is larger, making the measurement at 400 feet appear electrically closer to the antenna. Here are the azimuth patterns for the top-mounted example on the previous slide. Unlike the side-mounted examples, these patterns are unobstructed by towers or support poles in the aperture of the antenna. So what does this data tell us about the functionality of these antennas we've been measuring? We know that the far field pattern calculated in HFSS matches the factory measurement of the antenna. And we know that the HFSS near field measurement matches the drone measurement of the antenna. Therefore, it follows that the measured antenna is operating as expected in the far field. To summarize, this near-field drone measurement technique can be used to ensure the azimuth footprint and orientation of a given antenna, as well as confirm the beam tilt and null structure of the elevation pattern. This method provides a quick, easy, and cost-effective way to validate antenna operation in the field. Thank you very much, and I will take your questions now.